Okay, in this example we are going to take a look at assemblages of pulleys. A big key thing here is that we're going to assume no friction present. Right? That is not necessarily always realistic, but it's not too bad either. But it does help things quite a bit. Now the other thing that we're going to have to recognize is that with no friction present, one of the implications is going to be that the cable force is constant along its length. So when you're doing these pulley problems, you got to look not only at counting how many pulleys do we have here, but we also want to look at, well, how many different cables do we have? And here we got 1, 2, 3 cables. So there's actually different cables running around, 3 different cable forces running around, right? We got a 200-pound weight. We already have the weight in force units, so there's no W equal mg here to have to fuss with. So there's your applied force, and here's the T to hold that system into equilibrium that we're after. Right, so there's a lot of things you have to be careful of here. One of is paying attention to how many pulleys you've got, how many cables, and their orientation. All the cables here, except for right around the pulley, are all somehow got vertical segments. And once you do these a lot, and you understand the mechanisms, you could actually get to this answer in about one step, because it's sort of a simple counting thing. But to prove or derive or to explain the basis, well, you know, what the heck, let's just see. We've got 1, 2, 3, 4 pulleys. Let's just say, let's as a guess, say, let's take T to, that T has to be equal to 200 pounds divided by 4. That would be 50 pounds. We'll see how close we are, right? Because it's a guess, let's put a little squiggly line over the top of it. Just see what happens. This little underline was just a mistake. That's an erratic. Alright, now the way you do this and really figure it out is go and do free body diagrams of the individual pulleys. So let's label them A, B, C, and D. And we'll just start then with, and I want to preserve some space on the page. Of course, I ask you to use as much engineering paper as possible, but you guys never do that anyways. Alright, so free body diagram of A. And so we get out a circle template. See if I can find my circle template. Here's one, here's another. Let's use this one. And there's our pulley. We've got then the 200 pounds that just translates directly right up its line of action. And so we can put it right here at the center of rotation, which is where it's hanging from. 200 pounds. Right? Then we've got, carefully now note, vertical force here and vertical force here, because we've cut right through there. Right? And freed out that pulley. So that one we'll call T1. Hey, how about we call it TA, since it's the cable wrapping around the pulley A. A? Canadian, eh? Alright, so we've got sum of forces in the Y. Again, no X, no movement sideways because we have no forces in the horizontal direction. Now we'll take upwards as positive, so we'll have 2 of the TAs. Notice, constant cable force. If we had friction, these 2 cable forces would not be the same necessarily. Right? 2TA minus 200 will equal 100 pounds. Oops, what? I'm getting ahead of myself. That equals 0, and therefore TA equals 100 pounds is what we're looking for. Tension, right? Pulling away from the free body diagram, else we got serious problems. You say you can't push on a rope. I say you can. It's just that it's going to move a whole heck of a lot if you do. Alright, we'll go to the next free body diagram. Now, we could be clever, I suppose, and cut all the way through here, but why not instead just isolate the pulley B? Right, and go through there. When we do that, then, let's see, what circle did we use? Not that one, not that one, yeah, not that one, 15, 30 seconds. Alright, so now we'll come in, take that circle, that's, ouch, that's going to be of pulley B. Note, now this little cable, this right hand side, that's now pulling down on B at 100 pounds. And we've got the then cable coming up. That's a new and a different cable, so it has to be different. There's TB, TB, and wouldn't you know it, that's going to be this almost identical free body, or well, almost identical free body diagram, and of course the equation is highly similar. 2TB minus 100 equals 0, and therefore, get the colors right this time, TA equals TB equals now 50 pounds. And I'm going to squiggle out that little line. That looks like a force arrow, and that's not what I meant. I meant to just underline or highlight it as we got here. All right. Wow, it got smaller. We're already down to 50 pounds. It looks like the guess is going to be wrong, isn't it? All right, so now we'll go and do free body diagram of C. And when we do that one, same thing. Right? Man, we're going to probably split in half again, aren't we? It's kind of interesting. Seems like every time we're going around a pulley in this kind of condition, we're splitting the forces in half. That's very interesting. So there's your 50 pounds that we got going between B and C. That was really TB, and now we have TC. And, well, gosh, you know, it's getting the feeling of the pattern here. And alright, plus, go up, positive sum of forces in the y, 2TC minus 50 equals 0, therefore TC equals 25. I got the color wrong again. And of course pounds. Alright, so now, gee, do we have to really do this last free body diagram? Because note what happens. It's the same cable all the way around. So our final answer has to be that TC is T, and that our answer is 25 pounds. Right? Now you might say, well, hold on a second. There is, you know, we were splitting the force. It was doubling, and you didn't. What's going on here? Well, let's look at that pulley. That is pulley D. And note what's going to happen here this time. It's a little bit different than we had before. All right, because we have now TC, that's the 50 over here. We've got T on the other side. It's the same physical entity, and with no friction, that has to be equal to 50. And so this is the reaction over here for the pulley at D, and by sum of forces in the vertical direction, that's the one that gets doubled rather than splitting here. So that last pulley is just acting a little bit different than what was going on with the other system. All right, so that's one big thing. And then let's go back and talk about, hey, I just guessed 200 divided by 4 was, you know, because I had 4 pulleys. So hey, I'm splitting it 4 times. Well, it doesn't quite work that way. You have to follow the equilibrium that we've got. We do have a splitting, and then a splitting, and then a splitting. So this averaging says that the overall, the smear it all out, it all happens the same, and that's not quite what happens. We reduce by half, then we reduce by half, then we reduce by half. So a half of a half of a half is 1/8, and 25 is 1/8 of 200. Don't believe me? Then let's do it. 25 divided by 200 is 1/8, right? That means that we're putting in 1/8 of the force to lift something, or the other way to look at it is, I put in 1 pound here, I can lift 8. That's a mechanical advantage, and mechanical engineers are really concerned about that. So mechanical advantage would be what force out do we get compared to the force in, and in this case we put in 200, or rather we got out of it 200, we put in it 25, and that's a mechanical advantage of 8. That's a very nice ratio at the cost of having 4 pulleys and some cabling systems.